Hi everyone, we're going to be talking today about electrons as waves. So the first thing I want to discuss really is how are electrons going to act as waves? Because it's a weird thing to think about. Pretty much every model of an atom you've ever seen so far involves the nucleus and the electron kind of traveling in this circle around the nucleus. But in my electron configuration and orbitals lecture, we talked about them being in specific areas around a nucleus, not just traveling in a concentric circle. But unfortunately, it's even a little bit more complicated than that, because while you probably have thought of electrons just orbiting in that concentric circle, what they're actually doing is behaving like a wave of light, and traveling in a wave pattern around the nucleus instead. So I've included both of these pictures to just kind of show you what we think of versus more of a close representation about what's actually going on. But you see these little n equals 1, n equals 2, n equals 3 showing up in both representations. And that's representative of the different energy levels that an electron could be located in. So what I mean by that is, when I'm talking about energy levels, think about your electron configurations: 1s2, 2s2, 2p6, all of these things. The 1 and the 2 and all of those things, the big numbers, those are representing the energy levels. Or you can think about them most closely represented to what period each element happened to be in. But with that said, one atom can have electrons in multiple energy levels. So depending on which energy level any particular electron happens to be in, that's what that n equals 1, n equals 2, n equals 3 means, okay? So the next thing I want to discuss is light emission by electrons. So electrons are not bound to only remain in the energy level that they're assigned to in their ground state. They can jump around to different energy levels and do, which we're going to see in the flame test lab. So let's say you stick atoms under a flame. That flame is releasing a lot of energy, and those atoms are going to absorb that energy. Their electrons will absorb that energy, and when that happens, they're going to climb in energy levels. So that's what this yellow up arrow represents here. That electron is absorbing energy and climbing to a higher energy level. But if you recall, I told you already that an atom cannot maintain electrons in that high energy level because it's not sustainable. So eventually, that electron will fall back down to its ground state energy level. And depending on what level it fell from and how far it is falling, how many energy levels it crosses when it falls, different types of light will be emitted. So that's what this is representing over here. An electron that's falling all the way from level 6 to level 2 is going to emit violet light. If it's falling from level 5 to level 2, you're going to get blue. From level 4 to level 2, you're going to get green. And from level 3 to level 2, you're going to get red, which should make sense because, as you probably learned in middle school, red light is the lowest energy level light. Violet light is higher frequency, higher energy light, and so on and so forth. So that's where that's coming from. And this down here is really saying the same thing, okay? But it's a little bit more clear, saying the electron itself is not colored blue. By falling from one energy level to the next, it's emitting blue light with a specific wavelength and frequency and energy. And if it's falling here, it's going to emit green light, okay? So that's what the flame test is really demonstrating, because each atom has many electrons, but each atom also has a very specific amount of electrons. So depending on how much energy you put into the atom, those specific electrons will absorb specific amounts of energy and fall to their own ground state, therefore emitting distinct light colors. So here's here's an example of some elements in the colors of light they tend to emit. But you will see that for yourself when we do the flame test. So next, I want to get into the meat of why we care, because we're not just going to look at the pretty colors that are emitted when you expose atoms to higher energy levels. We are going to take that information and we're going to do calculations with it. And to do that, we really have to talk about the characteristics of waves themselves. So the first characteristic is wavelength, which we represent with this Greek letter, lambda. So it looks like an upside down Y. That is going to be how I will represent wavelength or abbreviate wavelength. I will refer to it as lambda, and I do expect you to realize that when I say lambda, I'm referring to wavelength, or when you see this little upside down Y, you know that I'm referring to wavelength. So what wavelength is the shortest distance between equivalent points on a continuous wave, either crest to crest or trough to trough. And that is measured in meters, okay? So if you are looking at a measurement of wavelength and it is not in meters, chances are you're probably going to have to convert that to meters to do your problem. So before I move on, I'd like to just make a little bit of a drawing for you, and this is going to be a little bit messy because I am hand drawing it. But if you're talking about a wave, and I'm trying to make this even-ish, what I mean by a crest to crest and a trough to trough is this distance right here is a crest to crest, because the top of a wave and the top of a wave, those are both known as crests. Trough to trough is this measurement right here, or the other end, the bottom. So assuming that my drawing skills are beautiful and lovely, those are going to measure the same thing. So you'll see that in actual picture representations of waves. But when I say crest to crest and trough to trough, that is in fact what I am talking about. Okay? So moving on, I just want to go over this power of 10 prefix abbreviation table really quickly, because very often meters is going to have a prefix attached to it. Picometers, nanometers, micrometers, millimeters, kilometers, megameters, gigameters, terameters. You are responsible for knowing or being able to look up what those abbreviations mean, or if you see micro, nano, pico, kilo, whatever, you do have to know what those letters mean. So just take a quick look at this table and familiarize yourself with it. The next characteristic of a wave that I want to talk about is frequency, which is represented by this Greek letter right here known as nu. So it's going to look kind of like a V. So often when I'm just drawing problems, you'll just see me put a V. That's what I'm talking about when I write that little weird V, is frequency, or nu. Again, you are responsible if I say nu to know that I'm talking about frequency. Frequency is the number of waves that are going to pass a given point per second. So when I draw out a wave, waves don't just stand, they're not just still in the air, they're traveling. So let's say we picked a point and the amount, that wave is going to be traveling past that point. So the amount of these waves that travel past that point per second is its frequency. And we measure frequency in hertz. Hz is the abbreviation for that. 1 hertz is going to be one wave passing a point per second. So it's a 1-to-1. If I were to tell you 4 waves are passing a point per second, well, that's 4 hertz. If I tell you 10 waves are passing a point per second, that's 10 hertz. There's not going to be a conversion that you need to know how to do. It's just, if I tell you however many waves are passing that point per second, that's how many hertz you have. Okay? And then we have amplitude next, which is described as the wave's height from the origin to the crest or from the origin to the trough. So let's go back to my super great wave drawing, and let's pretend that this is even. Waves are described via amplitude from the origin. So if you're looking at this on a graph, the origin is going to be drawn like that. And so when you're measuring the amplitude, it's how high it is effectively. So this distance right here or this distance right here, which again, assuming I could draw better, would be the same. Okay, so that's amplitude. Here is a picture with all of those things together. So we have our amplitude, which is again origin to crest, or it could have been origin to trough down here. We have wavelength, which in this case is crest to crest, but we could have measured it trough to trough down here. And then frequency, let's imagine that our point that we're picking is here. And if this wave were traveling, how many waves would pass that per second? Those are the measures when we are talking about waves. Okay? So one thing that you do have to be aware of is as wavelength increases, frequency decreases. And the opposite is also true. As wavelength decreases, frequency increases. And the reason for that is because most of the time, when we are talking about waves, we're talking about light waves. Most of the time. Not always, but most of the time. Light travels at a very specific speed. Okay? But light can have different frequencies and different wavelengths. So, if the wave is bigger and it's traveling a certain speed, less waves are going to pass whatever point in per second. But if you have something with a higher frequency and a smaller wavelength, you're going to get more of those waves passing that point per second, assuming that both the waves are traveling at the same speed. Okay, which is weird to think about, and I know that. But as we do problems, you'll see that mathematically that does work out. So here's the mathematical relationship of electromagnetic waves. We have the wave's speed is going to be equal to the wave's wavelength times the wave's frequency. Speed equals lambda nu. You'll hear me refer to this equation that way. You'll hear me call it the wavelength equation. I'll call it a bunch of things. But you have to know speed equals lambda times nu. Speed equals wavelength times frequency. And that's what this is here for. Okay? One number that you do have to be aware of is this speed of light here. Because again, most of the time we're talking about waves, we're going to be talking about light waves, and light always travels 3.00 times 10 to the 8th meters per second. 3.00 times 10 to the 8th meters per second. So if we are ever talking about light waves, you are going to fill in this number for speed. Okay? There are other options for problems. I could tell you that it's not a light wave and it's traveling a different speed, in which case we'd use that for speed. But if we're talking about a light wave, it's going to be traveling 3.00 times 10 to the 8th meters per second. Okay, so here's a sample problem that I'm going to walk us through together. If a gamma ray traveling at the speed of light has a frequency of 2.88 times 10 to the 21st hertz, what is its wavelength? So the first thing that I'd like to do is I'd like to go ahead and rewrite that equation that I just used before. Remember, speed equals wavelength times frequency, okay? So if we look at this problem and we read it carefully, most of this information that we need to solve it is already given to us. If a gamma ray traveling at the speed of light in the previous slide, I told you what the speed of light was. So immediately we fill in that number for speed, which in this case is 3.00 times 10 to the 8th meters per second. Okay, so we just filled in that number for speed. It has a frequency of 2.88 times 10 to the 21st hertz, okay? Hertz, as we learned, was the unit for frequency, and it told us its frequency. So for nu, for this little v here, we're going to fill in this number, which leaves wavelength as our variable because it's asking for wavelength. So we have the wavelength, that little upside down y, times 2.88 times 10 to the 21st hertz. Okay? Now, how do we solve for a wavelength? We are going to divide both sides by this number because we're trying to isolate lambda. Okay, so we're going to divide our right side by 2.88 times 10 to the 21st hertz, and we're going to divide our left side by 2.88 times 10 to the 21st hertz. Okay, if you divide something by itself, cancels out. So we end up with lambda equals whatever this is. Now, recall, I taught you how to divide using scientific notation. Okay, you don't need to plug in 3.00 times 10 to the 8th divided by 2.88 times 10 to the 21st into your calculator. You could, and it would definitely get you the answer, but that's assuming that you plugged it in correctly. And every calculator is different. So unless I'm standing in front of you, I can't tell you whether or not you plugged it in correctly. So my advice to you is use the skills that I taught you to do this problem. So if we recall, when we're dividing numbers like this with scientific notation, we have the opportunity to divide our raw numbers. So divide 3 by 2.88, and if we do that, we get 1.04, and then we're going to add in times 10 to the something. And if we're dividing exponents like this, you subtract your exponents. You take 8 and you subtract 21. If you do that, you get negative 13 as your exponent. So that's a quick way to do it without having to plug in all of this mess into the calculator and worry about parentheses and all of these things. Okay, all you had to plug in your calculator was 3 divided by 2.88. So the last thing I want to talk about before I move on to the next problem is, do our sig figs match? We have 1, 2, 3 sig figs here. We have 1, 2, 3 sig figs there. Our answer has 1, 2, 3 sig figs. So our sig figs are good. We did the problem. This is our answer. But we have to include units. And if you recall, the wavelength is measured in meters. So our unit for wavelength is going to be meters. Okay? So next I want to talk about the energy equation, which is the only other equation that I'm going to talk about right now. Our energy equation is E equals H times nu. Okay, so E is energy. So the energy of a wave is equal to H, which is something called Planck's constant, which is always going to be this number, times whatever that wave's frequency is. Energy is equal to Planck's constant times frequency. If ever you're using this equation, H is always going to be this number. That is not going to change ever. So a lot of times when I see students doing these problems, they always forget that H is a given number. It is a constant that does not change. It is 6.626 times 10 to the negative 34th joules seconds. That does not change. So don't ever worry about that being a different number because it will not be. So we have another sample problem here, okay? All right, so once again, I'm going to rewrite the energy equation. E equals h times nu. Energy equals Planck's constant times frequency. Okay, so once again, all of that information that you need to solve this problem is given to you. All right, so the first thing that we need to do here is we need to start plugging in information where it goes. It says a photon has an energy of. So right away, we're told what E is. So we start plugging that in. We have the 2.93 times 10 to the negative 25th joules equals Planck's constant times frequency. Now notice it doesn't give you any other information because Planck's constant is a constant number which you were already told. So we have 6.626 times 10 to the negative 34th joules seconds. Okay? And we multiply all of that by our variable, that V, for frequency, because this is what we're trying to figure out. Okay, so we're going to solve this the exact same way we solved the other one. We want to isolate our variable, so we divide both sides by Planck's constant. We're going to divide this one by this number. We're going to divide the left side by that number. Okay, once we do that on this side, this goes away, and we have this division happening. So once again, you have options. You can either plug this into a calculator, which again, I would definitely not recommend because once again, you may make a mistake plugging it into your calculator. So my advice to you, instead of plugging it into your calculator, is you just, once again, you're going to do that raw number division and then do your subtraction, and then we convert it to an appropriate scientific notation form, okay? So if we plug 2.93 divided by 6.626, you're going to get 0.442. You get this. There are more decimal places beyond that. However, if we pay attention to our sig figs, we have 3 and 4, so our answer has to have 3 sig figs, which this does. Okay, then we're going to have times 10 to the something, and we have to subtract our exponent. So we take negative 25 minus negative 34, and we get 9 equals this, okay? However, this is not proper scientific notation, so we have to convert it into proper scientific notation by just moving that decimal place over 1 and changing our exponent. So you can rewrite this as 4.42 times 10 to the 8th equals your frequency. Once again, you have to add a unit, so make sure that you put hertz as the unit because frequency is measured in hertz. And I apologize that this was here. This wasn't supposed to be here because it's part of the problem, but this is how you're going to do one of those equations. Now, last but not least, I could ask you to put the two equations together using both of them. So I'm going to rewrite both of them up here. We have speed equals lambda times nu, or frequency, and we have E equals Planck's constant times nu, or frequency. So these are our two equations that we might have to put together. Okay, so our question says, what is the energy of an ultraviolet photon that has a wavelength of 1.18 times 10 to the negative 8 meters? Now, it's asking about energy, but it gives you wavelength. So if you look at this equation, wavelength is nowhere in the energy equation. So what you have to do first is you have to find the frequency so that you can plug that frequency into your energy equation to find your answer, the E. So we're using both equations and those will show up. All right. So the first thing that you want to do is you want to start with whatever you're given. We are given wavelength, so we're starting with the wavelength equation, this one. So if I'm using speed equals lambda times nu, I'm given lambda, I'm given the wavelength, so I'm going to plug that in, 1.18 times 10 to the negative 8th meters. Okay, I need frequency because I need frequency to be able to even use this equation later. I am not directly given speed. However, ultraviolet photon, you see the word photon, that is light that it's talking about. And since it's light, we're going to use the speed of light, which if you remember from previous slides is the 3.00 times 10 to the 8th meters. Okay, so now we have a solvable equation. We can solve for frequency, which we're going to do by dividing both sides by this number to isolate frequency. So we divide by 1.18 times 10 to the negative 8th. We divide this side by 1.18 times 10 to the negative 8th. This goes away. And we just do this simple division here to get our frequency. Okay, so if we do this on a calculator, you could once again either plug this in or you could do the trick I taught you. So if you divide 3 by 1.18, you get 2.54. And again, make sure that you stick with the amount of sig figs you need, which in this case is 3. Then we have times 10 to the something. 8 minus negative 8 is 16. So that's going to be our frequency. Now, when we move on to the next equation, I'm just going to kind of draw a line down so that we don't get confused. We have to take this frequency and plug it in to the frequency equation to find our answer. Ultimately, this problem is asking what is the energy, so we're looking for E. We know what Planck's constant is, the 6.626 times 10 to the negative 34th. And we just figured out what our frequency is, our 2.54 times 10 to the 16th, okay? And yes, that is in hertz. I had forgotten to write down the unit over here, but it is hertz, all right? So to solve for E, all we have to do is multiply. And when we're multiplying, again, I urge you to just multiply your raw numbers and then deal with your exponents so that you don't run the risk of plugging it into the calculator wrong. So when you multiply 6.626 times 2.54, we get 16.8. And yes, that is rounded because 2.54 has 3 sig figs, so we needed to round that off. Then we have times 10 to the something. Negative 34 plus 16, and we are adding because this is multiplication, equals negative 18. So that's going to be your exponent. Once again, this is not proper scientific notation, so we have to rewrite it. We just move that decimal place over 1. We have 1.68 times 10 to the negative 17. Okay, so that's how you're going to rewrite that, and this is going to be your final answer. Energy is measured in joules, so your unit is going to be in joules. Okay, so I hope that that was helpful for you and that you won't have too much trouble with these wavelength and energy calculations, but we will be doing quite a bit of practice in class. So if you are ever unsure, feel free to ask me.